Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll learn how we as engineers can tackle noise control problems when we are tasked to tailor room acoustics.
So let's get started. We know through experience that our day-to-day environments can be drowning in noise, whether this is in a restaurant environment or a bustling factory space. This can be a nuisance on one hand, and at the other extreme could be life-threatening if we're unable to hear dangers that are impending. So optimizing an interior acoustics is a significant part of those involved in the construction, architecture, design, and engineering of interior spaces. Leading this effort should come early in the design process, especially for commercial and industrial spaces. The OASPL and the reverberation time are the important metrics to tailor for room acoustics. The recommended OASPL for the room use is related to the speech interference level, SIL, and the noise criterion, NC, keeping in mind that early onset hearing loss occurs for OASPLs of around 85 decibels and up. For the reverberation time, it also affects room use, and tabulated T60s can be found in many resources. Sound transmission, though, is not explicitly defined. This is because the sound transmission is not the only indicator of the OASPL in the room. The SIL and NC together help inform us as engineers on the optimal transmission loss of walls and interior surface qualities that help achieve the OASPL targets. And frankly, depending on where the troublesome noise originates, whether in or outside of rooms, we may or may not even focus our attention on optimizing transmission loss as a key indicator of that room's acoustics. Changing the TL of a wall can be achieved by much more than change of the wall material. Take, for instance, the approach of eliminating the direct sound transfer path, whether through resilient connections between the drywall and the studs, or through the use of redundant structural supports. These are ways of using minimal extra mass but achieving significant improvements of transmission loss. Similarly, IIC of floors is enhanced by removing the direct transfer path, whether through staggered floor joists or by putting interfacing layers of damping materials under the floor media. But all of this attention to detail could be for nothing if we are faced with a flanking path. Flanking refers to the weak links in the sound transmission path that result in disproportionately large influence on the overall sound transfer due to extremely high transmission coefficients. This results because of the logarithmic conversion between the power transmission coefficient to the transmission loss. This also affects transmission between floors inasmuch as it affects transmission between walls. Flanking comes in many forms. So far we've spoken about the gap under a door, which is a great example of flanking. But there are many examples of flanking that are faced by engineers day to day. Take, for instance, room dividers that don't extend to the ceiling or to the floor. There's multiple inches of gap here at the floor because the room dividers are mounted on rolling casters, and the room dividers don't even come close to reaching the ceiling. In this case, this elementary school will not be much quieter with the introduction of these room dividers. We also see flanking with shared floors between rooms. Drop impact noise from walking or objects would pass straight from one floor and into the other room, since this floor board is shared. That's why separate concrete pads and separate plywood boards are often used to insulate the sound from one room to the next. Wall penetrations that are used for electrical outlets and utility outlets are another source of flanking. When the drywall is cut larger than what is needed for the shape of the penetration of the outlet box, sound can easily pass the whole way through that wall with little resistance. Direct or straight HVAC connections between rooms are easy ways for sound to leak from one space to the next. Old homes that relied on furnace heating often used these from the basements up into higher floors, but it also allowed direct passive sound from one floor to the next. Gaps around windows, doors, whether in residential settings or automotive settings, are simple sources for flanking. The shared trait of these flanking examples and others are that they inadvertently short-circuit the transfer path, ruining our good intentions for sound transmission loss. In fact, the term flanking derives from the maneuver in battle to initiate surprise attacks at the side or rear of an opponent. Flanking maneuvers were often conducted with horse-riding cavalry soldiers. These would attack around the side of the main front. So take, for instance, one example in the American Civil War at Gettysburg. Longstreet's force flanked Meade's rear. Sykes, the cavalry for the Union soldiers, responded. This is a very common maneuver in a lot of historical battles, but in acoustics, flanking can ruin an otherwise very well executed design. Planning and attention to detail will prevent flanking and help ensure that our designs help eliminate weak links in the transmission path. To summarize what we've learned, we found that the room use dictates the permissible sound levels according to metrics like SAL, the speech interference level, and the NC, the noise criterion. Achieving these sound levels, given anticipated noises in and outside of the room, is up to consultants, engineers, designers, and architects involved. And an essential part of success to achieve these sound levels is to avoid these weak links in the sound transmission path to ensure that our acoustic spaces are appropriately insulated.
That's it for this video. Now that we know all about how to control noise in rooms, in the next video we'll dive more deeply to learn about the many ramifications and consequences of how noise affects people.